Hello, everybody. Let's see. So this is the fourth video in this series. I don't know what the series is about yet. This is the second video in the series, the fourth video overall. I'm going to be talking a little bit about this Base62 encoder. If you tuned in last time, we were talking about creating this Base62 encoder and how I created a version in Java, Scala, Clojure, Go, Rust, Python, and a few other languages, and what that is. And basically it would be I think a good way to kind of compare some of these programming languages and show the differences and the similarities if you are so inclined. So it's simple enough where it's just going to be a couple of pages of code, so it'd be easy to kind of compare and contrast, for example, the Scala version, the Java version. So what we did here is we just implemented a Base62 URL, Base62 encoder. These get used for URL shorteners. So if you've ever used Bitly or TinyURL or any of the others, then you'll know what a URL shortener is. If not, there's this Wikipedia page, and you can read all about it. These are the different URL shorteners, the most common ones. You have Twitter, TinyURL, Wikipedia, YouTube, Bitly, Google, TinyURL, we mentioned that. Some of these get used internal, so if you use a really long link on a Twitter service or a Google service, they'll shorten it for you. And yeah, that's basically what a shortener is. So what a shortener does by default is it takes a number and it converts it to basically a series of numbers and letters, Base62. So it's every number, every capital every capital letter and every lowercase letter. Then you have, okay, so we talked about the Base62. So, and if you look at the code, that's how our code is structured. So there's a couple of articles I linked to that got some nice diagrams. Here's a diagram from one of them. Talks a little bit about how, so this is a dzone article on how to implement a URL shortener. There's another one, inext.io. I like this diagram. It's a little simpler. The article's a little longer as well. Yeah, so you use the shortened URL, and it's going to basically look that up in the database, and then it'll return the longer URL and do a redirect, more or less. Again, you can read about these and how the generation works, and essentially you do the 62-bit you do the 62 base conversion, and then you can store that. Let's just show an example. So here I have this book that I wrote a while ago, and it's got this really long URL. Let's pretend like I want to share this. So I'll go over here to Bitly. I'm going to create a new link, and I'm going to put in a link, and I will hit create, and you could see this little bit right here. I'll just blow that up. You blew it up a little too much. Yeah, right there. So that 3M let N9. So Bitly would create this Amazon link. Apparently they have a deal with Amazon. That's pretty cool. I didn't know that. That was I just learned this second. But anyway, so this is the short URL, and if you click on that, it would take you to the long URL. So if we copy that, we go over to here, paste it, and then that would become this really long URL. So the short one's nice. It keeps the text short if you're going to send it in a text message or a tweet or whatever. And you could potentially even remember it and type it instead of this really long multi-hundred character URL. Okay, so that's the basis. So I got a little program that does that. So let's take a look at that. Interesting. IntelliJ, here we go. So I've written this, like I said, a few different ways. First I wrote it in Java, and then I converted it to Scala, and then I made it functional Scala. Then I said, well, let me do a functional Java version, and then I used some features from Java 17. So I have 3 Java versions, a couple Scala versions, and Rust, Python, and a bunch of other languages. Go. I'm not telling you to go away, but the language Go. So, so essentially, I can give it a number. It'll give me a string. I can then convert that string back to a number. When we print this out, you'll see that both of those are the same number. So convert it to a string, convert it back, and I'll get this number both times. So if I had a URL like this is like the Amazon one. Ooh, really long. That is actually the Amazon one. I just changed the front end of it. And I get an ID by getting the hash code of that string. I create a short handle to that ID by using that number. And then I print out what that looks like. So if I run this, see if it runs, because I was editing it. You never know. So this is, if we go back up here, this is this number. And then this is what gets created from that. That's the short URL, if you will, part of it anyway. And that is the number converted back. So we go convert to string and then convert back to long. Okay. And then what do we have here is, here I take this really long URL, I convert it to a hash code, and that's this hash code here. I convert that hash code to a string, and then we just use that string instead of the long URL, and you could use it with a URL shortener. So that's basically what a URL shortener does. Now I have a table, pretty simple. I've got digits, and just like in the Wikipedia page, these are different place values. So every index is actually the value. So 0 is value 0, A is value 10, small a is value 36, and M is 48. And you could add additional characters if you wanted. Let's walk through some of this because we're going to walk through it in different languages and compare and contrast. It's a short program, so it should be easy. We've got this convert to encoded string. Convert to an encoded string calls find start bucket. Find start bucket finds basically what bucket that value is in, right? And then once we find what bucket, what range it's in, it's less than this, greater than that. So this calculates the current position, if you will. We could actually was thinking about a future article where I do some perf testing and compute these ahead of time and to speed things up, but I haven't done that yet because I wanted to show this version first. Maybe that's something we'll do for a future article. We'll get some perf tools and talk about how to increase the performance. But yeah, that's a future article maybe. So this is the power digit space. It's just going to do a power operation and then see what value we show up in. And again, if we compute those ahead of time, it would be a little faster. Actually, I have both versions. I've implemented both ways, and it is quite a bit faster, but we'll cover that in a different article. Bucket value is the value of the current bucket. Accumulator is basically what we have left. So we're going to start subtracting. It should really not maybe be called an accumulator, but I call it an accumulator. It's the opposite. We're basically calculating the value, the value starts off as the ID, and then we're going to keep subtracting from it as we find a placeholder. So we find a placeholder, we get the value of that placeholder, we figure out what index that placeholder is in, and then we calculate the value, subtract that from the accumulator, and then we append the results to our string. We have a little builder, a string builder up here, and we keep doing that. Let's look at append safe. Pretty simple. If it's not 0, append. Otherwise, seems like it does the same thing either way. I'll have to think about that one. Anyway, the idea is it's not going to do a leading 0. That's what it is. So it won't do a leading 0 if the size is not there. So if it's not equal to 0, it does this. If it is equal to 0, it makes sure that it's not the first item, so we don't have a lead 0 or a 0 padded number. So that's append safe, and then we go to the next placeholder. Placeholder is sort of the digit in, so we start with the most significant digit, and then we go to the least significant digit, and the placeholder is basically what digit we're currently in. Once we get to the first digit, we redo the calculation, but this time we keep track of the remainder, and then we append the remainder. Remember, we look up the digits here, the value, and we append the remainder to the string. So that is the convert to encoded string, and that's the non-functional programming version for sure. And we'll show that in different languages. We'll start by showing it perhaps in Scala, and then maybe Clojure, and then we're going to, and we'll compare them. Then we're going to convert from a long back into the original number, right? So we're going to take that string and convert backwards, right? That's the string, this is the encode, and this is the decode, right? So convert long calls to array and then calls convert long. We can see what that looks like in different languages, how they work with strings, how they work with characters. They're surprisingly similar. I'll give you a little hint. Here's our convert long. What we do here is we compute the value at the current position, and then we keep adding that value to the accumulator. If you look at compute value, it's pretty simple. It finds the index of the digit in the table, so it takes the character, finds the value, and then finds the multiplier, and then multiplies the index times the multiplier. And what else do we have? That's pretty much it. You can see we've got the find index of digit in the table. It's looking for what the index is. So there's different ways to write that. Different languages have different ways. Some of them are pretty simple. And we'll, like I said, we'll try to do some of this in a more functional programming way as well. Yep, that's pretty much the whole code. It's not that big. So what we'll cover next week is we'll cover the, basically doing the same thing in Scala. Then we'll compare the functional Java version to the functional Scala version, and vice versa. So let's go back to, where are we at? URL shortener. So we covered that. This is how the application works. We looked at the diagrams, first video in the series. I'm going to put this in the show note page. I created a small link in bit.ly for it. You can see it says Base64Rick. So that's the link to this page. I'll put that in the YouTube video. And then we'll start comparing it to other languages next week. I'll do a comparison to the Scala version. I'll start with the non-functional Scala version, compare the Java version to that, and then I'll compare the non-functional Scala to the functional Scala, and then we'll compare the functional Scala back to the functional Java. Maybe we'll do a couple of those next week or next time. I don't know if it's next week or not, but it's coming up. It's the next one. All right. Let me know if you're interested in this. I will put the actual code here. I'll link to various code examples, and yeah, let me know what you think. Talk to you soon.